Over to you, Jason.
Okay. Good evening, everyone, and thank you, Marilyn, for spending some time with us. Appreciate it. We're looking forward to your presentation. Marilyn is a senior system engineer at JMP, a subsidiary of SAS. Sorry, based in Arizona. She has over 15 years of experience helping engineers and scientists apply advanced analytics to improve quality and optimize processes across diverse industries worldwide. She holds a bachelor's degree in business and a master's degree in economics from Eastern Michigan University, along with a Six Sigma Black Belt from Arizona State University. Marilyn also completed advanced studies in statistics at Penn State, as well as machine and deep learning at the University of California, Irvine. Fluent in English, Spanish, and Portuguese, she specializes in no code and low code analytics workflows and is passionate about enabling quality professionals to leverage modern statistical and AI tools to solve complex problems and drive continuous improvement. Please welcome Marilyn Wheatley.
Great. Thank you, Jason. Hopefully I can share my screen. I had to send a request.
Be good to go.
Should I just do it again? Okay,
Yeah,
there we go.
okay.
Got it. All right,
Mhm.
here we go. Perfect. Can you see my screen?
Yeah.
Yes, I can see
Yes.
it.
Perfect. Thank you. And thanks. So thank you again for the introduction. So my name's Marilyn. I'm a senior systems engineer at Jump. And so as Jason said, I work with scientists and engineers in different industries. And I work with people in the Rocky Mountains and throughout Latin America currently. I'm also part of the Phoenix ASQ chapter, so it's really nice to be presenting here. So in my role, I spend a lot of time working through real problems with people that are trying to understand their data, improve processes, or make decisions that they can stand behind. So it's rarely clean or straightforward. So what I'm going to show you today is based on that kind of work. So the goal is to walk you through an approach that's practical and something you can take and apply in your own environment. And we're going to build it step by step. And actually today's topic sort of ties into the supplier quality presentation from John Chody last month. He spoke about, as part of his presentation, he talked about incoming quality inspection 4.0, and he mentioned moving from AQL to 100% inline inspection. So that's the topic of today's presentation. I'll show you a practical example of how to build a point and click model for classifying defects. And you don't have to be a data scientist, you don't have to code, you just need your subject matter expertise. That's the most important, and then some software to help you out. So the software I'm using today, this is what it looks like in the main window when I first open it. Jump is a point and click analytics platform that's designed for scientists and engineers. So bringing in data from the web or different sources, blending them together, creating graphs, designed experiments, and point and click automation. I say that just because I want to let you know that what I'm showing you is not an AI automation tool. This is a tool for engineers that need to understand their data. And today I'm going to show you one example of what's possible in Jump. And I'll also mention that there are other software packages that do similar things, but this is the tool I'm familiar with and it's worked well for me. So let's jump right into it. But actually, before we build a model, I want to clarify what I mean by deep learning. So in traditional machine learning, there are two steps. First, you manually define the features from images, so things like edges, colors, shapes, and then you use those features that you extracted from the images, so features or X variables or factors, you use that information that you extracted to build a predictive model. And that feature extraction step requires a lot of manual work and subject matter expertise. On the other hand, deep learning is going to help, that's going to simplify this entire process. So with deep learning, the model learns both the features and the classification directly from the images. So instead of me deciding what matters in a picture image of what I want to classify, um, what we're going to do is label the images as defective or not defective. And when I say that we're labeling images, what I mean is we're classifying them as good or bad. Okay. And that's what I'm going to show you today, how to train a deep learning model using labeled images without manually defining the features or without having to write any code. So let's take a look at our case study. And this is a case study about defect detection in a metal casting operation. So let me tell you a little bit about the situation here. So pretend for a moment that you're the plant manager and you have a goal of replacing human visual inspection of a limited number of parts based on ANSI by automated visual inspection of all the parts using AI for appropriate classification. And the problem or the challenge is that attribute sampling could lead to customer dissatisfaction when the defective parts observed are greater than expected on the basis of the sampling. The rules can be a little difficult to follow unless you do that regularly when you're trying to reduce sampling, and could be prone to customer complaints about suspected quality decrease. And so for these reasons, as the plant manager, you want to use deep learning to build an AI classification model and deploy it to the production line. So let me tell you a little bit about the data set that we're going to use today related to these castings. All right, so I actually got the images of these castings from Kaggle. So let me show you. For those of you that aren't familiar with Kaggle, this is a platform where people share data sets and compete to build the best predictive models. And Kaggle runs competitions, and the top performers get ranked, sort of like chess rankings. So the tool I'm going to show you today was created by a Kaggle grandmaster. So that's a pretty elite level, a lot of expertise behind what you're going to see. So on this website, for this particular data set, we get a description, information provided by the person that uploaded the data set, and then there's always a zip file that you can download with the data. In this case, it happens to be images. And so let me tell you about these images before I show them to you. We have 4,211 images of castings that have a defect and 3,138 images of castings that have no defect. And that's what we're going to be working on. So let me show you the steps we're going to follow, and then I'll show you the images. So first, we're going to import the images into a data table. These are just JPEGs. We're going to clean and prepare the data. We'll create k-fold validation columns, and we'll talk about validation. We're going to fit a model, see a few things we can take a look at to evaluate it, improve, and repeat. And then we'll see some options for using the final model to make predictions. So that's where we're going. Now, let me start out by showing you a folder that I have with these images. Okay, so if I go into this folder, defective front, this is what it looks like. All of the pictures, whether the castings are defective or not, are stored in folders, and the folders are labeled whether it's defective or okay. Right? And so the first step is going to be to import those images. And to do that, I'm going to use JUMP. So I have an option to import multiple files. That's what I'll use here. And it's already, in this case, pointed to the location of the images that I showed you. And so what I'll do is, because my images are all in subfolders, I'm going to include the subfolders. And once I check that, down below, I can see all of my JPEGs listed. It doesn't have to be a JPEG. It could be a PNG or something else. The other thing I'm going to do is I'm going to choose to add the file name to the column or as a column in the data table so that we'll have the information, the labeling on which images are defective and which ones are not. And that's all I'm going to do for the first step. And what's going to happen is these images are going to get read in and they're going to be automatically stacked into a single column with all of the pictures. And since we have several thousand and I'm working on a laptop here, it'll just take a moment. So I've got some extra columns here that I don't need, and I'm going to go ahead and delete. So I'm just keeping my images. You can see the castings in the first column. And then here's that second column with a file name that I asked for. So
I have a question. Were these images taken? Were these images taken just for this effort, or they're ones that were already available?
right, so I got these images from the website that I showed from Kaggle.
Oh, I see.
Yeah. But they were taken to build a model like this, just not by me. So if you're thinking about doing something like this for yourself and taking pictures, that was actually good timing for that question. If you're thinking about taking pictures, you'll notice that these are pretty standardized in the way they were taken, but you do need variation, and you'll notice that there are differences in these pictures. So you're going to want to take pictures from different shifts, different operators, lighting, cameras, different types of defects, etc. So think about this sort of like sampling parts when you're doing a measurement system study, right? You need parts that are representative of the parts that your measurement system is going to measure in production. And so this is similar. The images that are used to train the model to classify good versus bad parts need to represent the variation of images that need to be classified in production. So that is important. And then you'll also need to make sure that the images are correctly labeled as defects or not defects. And a lot of projects fail because people are really focused on building the model, when a lot of times the bigger issue is the quality of the data that's being used to build the model. Okay, so we're going to use these
Can I ask a
images.
question?
Sure.
Yeah. So what if you have a picture where you're not sure whether it's defective or not?
You're going to have to decide because the model's going to learn from what you teach it.
Okay. So you need to classify them a priori, whether it's defective or not defective.
That's right. Yes, it's going to learn
Okay.
from your classifications and the images.
Okay. Thank you.
That's right. Yes. And I think that'll become a little clearer as we work through this. So the model that we're going to build is going to be a model using Torch. And Torch is an open source deep learning framework that provides neural network technology behind the scenes. And Jump Software is giving me sort of a visual interface so I can build this model without having to write to script in Python. And so let's start cleaning this up like any other data set. It needs a little bit of cleanup. I'm going to retitle this column defective or not. And then notice that this says defective front as part of this text string. I need to clean this data and just extract the section of the text string that labels the image as defective or okay. And so to do that, I'm going to use something called recode. I want to store the results in place in the same column. And what I want to do is I want to extract a segment of text. So this is how the text string currently looks. And I can use the sliding control to indicate what section of the text string I want to extract. And then down below, these are the current values in my labeling column. And here I can see the replacement value. So I highlighted the section that I want to extract. That's what I'm going to get. And that is what classifies the images as okay or defective. So I'll give an okay. I'll give a recode. And now that column is all cleaned up and I can use it to build my model. before I do that, I just want to show you that if I open this header graph here, if I click on defective front, just going back in the presentation, I told you I had 4,211 images that are defective front, and the ones that are okay, that's 3,138 images. Okay. All right, so we cleaned up a little bit of the labeling, the text. The other things that we might want to think about with the images as we're cleaning the data is I want to show you a few options. So if you wanted to manipulate the images, for example, you might want to see how big they are and if they're standardized, and you can quickly figure out how large are the images. So this gives you the pixels, the number of pixels. So these are all pretty standardized. You could crop images. That's another option in here that I want to point out. And that could be really important. I want to give you an example. I worked with a different data set that was for mining, and with some people that were trying to classify minerals, like as the minerals, the ore is coming out and out of the mine. And they took a lot of pictures to try to build a model, but the pictures needed a lot of cleanup because the way that they were taken wasn't standardized. Like some of them had a nice plain background, the way these images do, but some of them were being held in someone's hand and there were like pictures of like thumbs and fingers in there. And so you definitely want to avoid that kind of thing. And you can do that by cropping the images and making sure there aren't extra things in the images that could confuse the model. And we'll talk a little bit more about that later. All right, so our next step, we've cleaned up this data a little bit. We're gonna go ahead and create some k-fold validation columns. And so if any of you aren't familiar with the concept of validation, this comes in when we have the luxury of having lots of data. We wouldn't do this with little data sets. We would do this with thousands or maybe hundreds of thousands of images. Validation is the idea of using just part of the data to create the model and then holding back part of the data to test the predictions, to see how good they are, and then update the model. So we're sort of evaluating the model using the held out data while we're building it. So it's sort of like giving feedback to the system as it learns to classify the images. So let's do that. I'm going to go back in here and I'm going to make k-fold columns. And my response or outcome I want to predict is whether the casting is defective or not. And I also like to stratify by the response. And now this is the important piece on k-fold. So what this says is we're going to create 3 columns, and each of those 3 columns is going to have 5 groupings. Let me do that and then we'll talk about it. And as these columns are being created here or separated, this is actually a designed experiment that's getting set up in the back. Here we go. So let me show you these columns. Notice there's 5 groups in each column. So if we were going to do really simple validation, we might use 75 or 80% of the data to build the model and maybe 25 or 20% of the data to test the predictions. If we're using a deep learning type model, we're going to want to use different parts of the data and have several passes at it. And that's what these k-fold columns help us do. So for the column that's titled fold A, we're going to use groups 1 through 4, for example, to build the model, and then the 5th group to test the predictions. And then we're going to pass through again and maybe use groups 2 through 5 of the data to build a model and use group 1, the group that wasn't used, to test those predictions. So really we're showing the model different groups of images at each pass, essentially. And we're going to do that several times. through this sort of iterative process. Now, if we were really going to build the model, we would use all 3 columns and cycle through every group. And each group is going to be used both to train and test the prediction, train the model and test the predictions. But in real life, that takes a while. On my laptop, I'd probably have to walk away and go get some coffee and come back later. So I'm not going to do that to you. I'm just going to use simple validation. So this just split out the groups in this column into 5 groups, and I'm just going to use this one column for validation so that 5,879 rows down here are going to be used for building the model, and we're going to test the predictions on these 1,500 rows. And this is just to make it faster so we don't have to wait today. And the last thing I want to do, and you'll see why in a bit, I'm going to choose an option here that's going to help us see the images within the model later. All right, so now we have imported the images. We have cleaned and prepped the data. We've created the validation columns. Now let's get to the fun part, building the model. So I'm going to come back into Torch Deep Learning, and I'm going to pull this up. So the first thing I need to do is cast the columns I want to use into roles. And so the outcome or thing I want to predict is whether or not the front of these castings are defective. And the X or input I'm going to use is the column with the pictures. Remember, the algorithm is going to extract features directly from those images for me. And I told you we're going to use the quick validation so we don't wait all night. Give that an OK. And now in this window, this is where I can specify the model I want to build. At the top, this is just a summary of the options I've already selected. And what we're going to do with Torch to build these deep learning models is actually we're using pre-trained models. These are not models that were trained by JUMP. These are from Google and other companies. But these are pre-trained models that were trained on millions of images. And now we're basically refining it. So we're training the model for our specific use case with our own images. So down here, the first thing I can choose is the image model. So the image model is which one of these do I want to use to extract the features from the data. So there's models for small data, medium, and there's more that you can download for large data sets if you're running this program like on a server or in the cloud, probably. I'm going to use GoogleNet because I've had some luck with that, but you could certainly use the default options. Everything gives pretty good results, and then you can kind of figure out what to tweak as you go along. So what's going to happen is GoogleNet is going to extract the features or information from those images, and the way that gets extracted, it's going to be numerical data that's extracted from the images. And that numerical data gets put into a table that's then used to build the predictive model. And so those numbers that get pulled out of the images go into a table, and they go in as a tabular model. So there's different options for that. I'm just going to leave the default. Binary loss, just think of this as how we quantify the model error during the training. And so our goal is going to be to minimize this. And there's different ways to measure it. That's what these options are. Epochs, this is an interesting concept that's pretty unique. So epochs really just means how many times we're going to show all of the images to the algorithm so that it can learn to classify the images. And so more epochs is probably going to build a better model, but more epochs also takes more time. So I'm just going to do 5 for now. And the last thing I'll mention here, I'll just mention the learning rate. That's just how quickly the model updates itself in response to the errors. So basically how quickly the model learns from mistakes. There are other advanced options here. I'm not going to talk about those now, but just know that if I just hover my mouse, I can get a tip on all of these things. So you really don't need to buy a book on deep learning if you wanted to build a model like this. You can play around with it like I know engineers like to do, and then you can just make changes and see what happens. So I'm just going to leave everything else here, and I'll give this an OK. And it'll just take a few seconds, again, because I'm just running on the laptop. This is why we didn't use those k-fold validation columns. And now as this is being fit, I'm getting some information in this window about how well the model that I'm building can classify images. All right, so we're just about done, and that was 5 epochs. So let's take a look at this result. Let me expand the window there. Okay, so we still have all the same options at the top. And here it says model comparison because as we tweak the options at the top, that's going to create a new model, and we can just keep a list of the models here to make a comparison. So let's evaluate this model just a little bit. There's an R-square, which would be good if we were predicting a numeric outcome, but we don't want to look at this. We're going to want to look at accuracy since we're talking about a classification model, and specifically, we want to take a look at the validation accuracy. That's going to give us a better idea of how well the model can classify new images that weren't used to train the model. And this is pretty good. I mean, accuracy would, if it was 1, that's a perfect model that doesn't misclassify anything. So that's looking pretty good. And then down here, I've got an image that I can use to see the training history of my model. We talked about quantifying the error in the model or the loss. And so we're looking at how the error decreased over time. So this dotted line represents the training data. When we first started out, the error was higher, but as we gave the model more passes through the images, the error decreased. And the same happened with the validation data. As we went through the data more with the training data, as we saw the images again and again, the error was being reduced. And so what we'd probably want to see in an image like this is that line should keep decreasing until it's sort of flattens out and we can't do any better. And so to make an improvement, like I said, we could tweak the options up here. I'm just going to switch this epochs to 10, just so you can see if we go through the images just 5 more times, we might be able to make an improvement. And there are other knobs we can turn to see if we can make an improvement in the model. So this is the part that's sort of iterative. You'll build a model, you'll see how well it worked and see what else you could do to tweak it and see if you could make it better. And once this model finishes fitting, we're going to go through and interpret the results of the full model. But I just wanted you to see that we can compare, we can tweak and iteratively just kind of keep making changes until we find a model that's acceptable for the use case that we have with an acceptable validation accuracy. All right. Great. So now we've got model 1 and model 2. And in this case, it looks like going through the data a little bit more actually didn't make an improvement. There are different controls that we have. All of these are controls here. We could change the type of model if we want. And there's a lot more options under advanced. I'll show you that in a little bit. So if we're judging the models based on the validation accuracy, I'd probably go with this first model. And so what I'm going to do is just uncheck the second one, just so it's not cluttering up my results. I only want to see the model that I think is better for my data. So let's take a look at interpreting these outputs. So first of all, we have these actual by predicted plots. And for all of the output in this type of model, we'll want to evaluate the results based on the validation data. So how well can it classify images that weren't used to train the model? So what the model is doing, it's calculating probabilities to predict whether each casting is defective or not. And you can see that down here, defective or not probability, actual. And on the left side, this is the actual classification. So up top, we have the images that are okay, and down below, these are the defective ones. And so the probability predicted by the model, if it's greater than 0.5, so this side of the graph, these images were classified correctly. And if the predicted probability is less than 0.5, so this side of the graph, the images on the left side were not correctly classified. Okay. And so for those of you that haven't had a stats class in a while, the probability ranges from 0 to 1. And so if, for example, the probability that a casting is defective is 0.6, the probability that it's not defective is 0.4. So here I can hover over these images and actually see the image itself. And I might want to do that for anything that wasn't well classified. I can go back to my data table and maybe just investigate further, just get a subset of the ones I didn't classify well. The other thing we'd want to think about is which one is a worse mistake. And I'm going to say this is probably a worse mistake on this side, right? Because this means this was actually a defective casting that we labeled as okay. And so we might pass that on to the customer, right? And then up here, this is also not good. I mean, that's not making it to the customer because these were actually parts that are okay that we classified as bad. So this is our rework and our scrap. So this is obviously not good either, right? All right, so we'll think about that and then take a look at the images of the castings. Maybe based on your subject matter expertise, you could decide why maybe there was an issue with that particular casting. You know, maybe there was disagreement. Maybe it wasn't correctly labeled to begin with, which, as I mentioned, could cause issues with building the model. So you'll use your subject matter expertise to see if you need to make any changes there.
Quick question.
Yeah.
So the top one, the OK front, that is a producer's risk, correct? Because
yeah,
we
you
are
could look at it
classifying.
that way.
Yeah. So, and then the bottom one is a customer risk.
Right. The
right?
bottom is the defectives.
Yeah. Defective, but we are classifying it as okay or something because it's low probability. So if you have a low tolerance for that, if you say anything beyond 0.05 or something, we are going to call it defect, then we can reduce the customer risk, correct? Can we have different criteria for the bottom portion and the top portion?
No. It'll be the same cutoff because remember, the probability of being defective, it's at 0.6. The probability of not defective is 0.4. But you can change the cutoff. And thank you for the question, because that's exactly where we're going next.
Okay.
Here we go. Perfect timing. I swear, checks in the mail. That was perfect. Here we go. I want to tell you, first I'll tell you about the confusion matrices, and then we're going to talk about the decision thresholds and how we can change that. And that goes right to the question that you asked. So here, if we look at this confusion matrix, which is not as confusing as the name would suggest, we're going to look at it again in terms of the validation data here. So the same as the graph, on the left side, this is the actual category or how we labeled it, right? Defective or not. And then here's our prediction. So we had 827 defects that were correctly classified, and then one, like we saw in the graph, that was incorrectly classified. And then for the ones that are okay, 620 were correctly classified as okay, but we made 22 mistakes here, right? And so it's really just going to depend on the application and which mistake is worse. Now, I mentioned that we can change the decision threshold, and that's what opens up here. On the right-hand side, hopefully you can see this. I don't know why the numbers are white. They're a little hard to see, but it has the same information that we just saw in the confusion matrix down here. These are based on the counts, and this is the same information. It's just the rates, okay? And that's what we're seeing here as well. And so what you can do, as I mentioned, the cutoff for classification is 0.5. And here's where you can make the change. There's a little handle here, right? And so we're clicking and dragging this one way or the other, and these numbers update here. So depending on which mistake is worse for your case, you could adjust where you want that cutoff to be. So now we have 33 defects here. If I pull this the other way, we have just 13 mistakes on the OK fronts. So you could adjust that depending on which type of mistake is costlier or worse in your specific situation. And then last thing I want to mention as far as evaluating the model is just another graph here. These are the ROC curves. And so we'll look at the validation data again. This shows us the area under the curve for both the defective and the OK fronts. This area under the curve is a number that ranges from 0.5 to 1. A 1 would be a perfect model that classifies everything perfectly. And there's actually two lines here, a blue one and a red one, to represent the defectives and the OKs. And then again, 1 would be a perfect model, and 0.5 is this sort of diagonal line here. And so if you have a 0.5 for your area under the curve, that means that your model is as good as classifying good and bad at random. So you need to do something different probably. Okay, so that's evaluating the model. And again, there are tweaks we can make. But let's assume this is the model that we want to use to make a prediction. And so what I could do, I'm going to give you two options. First, let's do the quick and easy. Let's say that I have more pictures of castings and I just want to make a prediction right here and see it. I don't have more pictures of castings, which is why I'm just going to copy these first 5 rows and paste them down at the bottom. And we're going to pretend they're different pictures just so you can see how this works. And notice I just have the images here and none of the other data associated with that. So now in the same window where I built my model, all of these red triangles are menus with different options. And so from here, I can say I want to save the predictions. And that puts my predictions here in the data table. So for these castings that I just pasted in there, from the first 5 rows, which were all defective, they are classified as defective. So that's good on our model. It did a good job with those. But I'm guessing probably, even though that could be handy in some situations, you probably want to deploy something that's going to use this model to classify defects versus not in real time. And so to do that, you can save out the Python scoring code right here. And so I'm going to do that. Sure, why not? There it is. Thank you. Okay, so here's the Python code to score this model, the scoring code for this model. So we could use this to make the predictions in real time. This could be installed on like an edge device, which is sort of like, I don't know, it looks to me like a Mac Mini, kind of a little box that runs the scoring code, and that could be attached to a camera. So as the images are coming off the production line, they're being photographed and simultaneously or immediately after they're photographed, classified using the scoring code. And even though this outputted that scoring code in Python, notice it was just point and click for me. I didn't have to write any code, which is great because I don't enjoy coding. And so those are kind of the options for deploying and using the model to make predictions. I just want to talk a little bit about AQL versus 100% inspection. Just as a quick comparison, right, with the sampling plan, we're only inspecting a sample. Here we can inspect every part. And there's other benefits, right? The algorithm's consistent, it doesn't get tired, and we could maintain a digital record of those predictions if we need. But just as important as the benefits that we get from this, I think it's important to talk about what AI inspection is not going to solve for us. So let's take a quick look. So the good things, yes, it detects defects, it classifies the images consistently. You can inspect every part and it gives digital traceability. However, and this goes back to one of the questions that was asked early on, it doesn't fix bad measurement systems, right? So quality engineers have been talking about measurement systems analysis for decades, right? Deep learning doesn't eliminate the need for MSA. So if humans can't consistently classify a defect, it becomes really difficult to train a model to do it consistently. So suppose you have 10,000 images and then you ask your inspectors to label the images. The first inspector says it's a defect. The second one says it's okay. And the third one says it's a defect. Who's right? Right? You're going to have to decide. So this really goes back to attribute agreement analysis, which is something probably a lot of you know a lot about. This is also not going to solve issues with poor lighting. So imagine a casting inspection station, right? You have a bright LED, the camera position is fixed, there's a clean background and your model's performing at 98%. 3 months later, the maintenance crew replaces the light. Now the shadows look different and suddenly the performance of the model drops. What changed was the inspection system though. So what could be happening in a case like this is that the model may be measuring the lighting conditions as much as it is finding defects. So that's analogous to changing a gauge or something else in the measurement system. Okay. So something to think about. Also poor fixturing. So suppose that every image was taken with the casting in the same orientation, right? What could happen? Say that like the model could start identifying the orientation of the parts depending on what they are. So like if you have all of the images of whatever widget it might be, all of the defects are rotated to the left and, you know, the non-defects are rotated right or something like that. The model could start predicting orientation and not what you'd intended. So in this case, for example, the model doesn't understand castings. It's just looking for patterns associated with the labels that you provided. And sometimes those patterns are not the ones we intended. Earlier, I mentioned cropping images. If there's like extraneous things in the picture, like fingers, that's going to be important because we don't want the image to be classified as good or bad, you know, because there was a finger in there, for example. And this is also in part where some of the model controls come in. So I mentioned earlier, there are advanced options here. And again, there's like hover help if you hover your mouse over it. But for example, there are options for flipping the images. So you might rotate the images, right, as you're training your model. And that would help you avoid that kind of mistake, like the model classifying based on orientation of the images instead of what you intended. And then last thing, of course, this isn't going to fix inadequate process capability, right? So if the line's producing 15% defective castings and management says, let's install AI inspection, you know, the AI inspection system might be great at finding bad castings, but the scrap's going to remain high, rework's going to remain high, and the costs are going to remain high. The inspection system finds the problems, right? It identifies the defects, but it's not going to fix it. And so as quality practitioners, we know that inspection doesn't improve a process, understanding and improving a process improves it. So AI inspection is no different. It's a powerful tool for detecting and classifying defects, but all of this still depends on good data. It still depends on clear defect definitions, aka the labels, and capable processes. And at the end of the day, this is still an engineering and quality problem. So none of this is going to work without your subject matter expertise. So just to summarize how we could use something like this in an inspection 4.0 system, we collected the images for model development and labeled them, hopefully correctly. I used JUMP to build and validate a classification model based on those images. And then I showed you options for deploying, including saving out the Python scoring code, which you could deploy on an edge device with a camera. And then optionally, you could store the predictions to continue monitoring and hopefully making improvements. And if any of you are thinking that this is something that you might want to do with a problem you're working on, I do have some examples I'm happy to share in the chat, but there are some engineers and scientists here that presented their use cases for deep learning. Here, Fangyi from, where was Fangyi from? She is from Procter & Gamble. And then there's another scientist that's predicting chemical formulations. That's David from Syngenta. So these are, scientists and engineers applying these tools, the same as what I showed you in their work and showing how they did it. So if you're interested, these people recorded their videos and I'm happy to share them with you. And with that, thank you. I'm happy to take questions.
Well, it's more of a comment. I think it's really important, like what you said, is you got to have good data. Otherwise, it's garbage in, garbage out. And that's why I was asking if these photos were taken for this purpose, because we need to make sure that we get good data. And my company, they're trying to use AI, but they never first went to check to make sure the data we had was even good, so.
Absolutely. Yeah, and these images were taken because it was from Kaggle. It was for model building. And these look pretty neat already. You saw they're like perfectly square and everything centered and a nice neutral background. It took work to collect all of those images, I would think. Yeah.
I was a little surprised by your comment, though, that said that it's good to have some variations to kind of represent, what different operators would encounter. Where I would try and make everything lined up the same angle, same lighting, just so we take out some of that variation. But I can see your point, how it's good to have some extra variation to represent what we'll see in the future.
Yeah, and Joshua, maybe I didn't say that very well. When I said operators and different things, I just meant make sure that the images represent the variation that you expect to be classifying off the line. So same as like an MSA, if you cherry pick the parts you use in a measurement systems analysis, you could make your measurement system kind of look better or worse. But if you really want to figure out where the sources of variation are, et cetera, you want to make sure you have parts that really represent, the parts that you need to be able to classify. And so this is just similar. Different types of defects on the castings, for example, should be represented. So I'm sorry if I didn't say that well before.
Thanks for the clarification. How long has this capability been available in the JUMP software? Because JUMP's been around for a long time, but I didn't know it was doing this kind of thing.
Yeah, I think this was maybe a year and a half or two ago. I was really blown away at first because I've been doing the manual feature extraction.
And then with other machine learning that's coming out, like Cloud Code and others, would their models be available to load into this and maybe get different results if we thought like Cloud could do a better job at analyzing the data or something?
There isn't a way to pull Claude into JUMP. this just gives you like a point and click interface to that Torch library, like I mentioned, but there isn't a way to bring in Claude specifically. There is there's an add-in called the Assistant that enterprises that have Jump use, and they can connect that to the LLM of their choice. So you can connect LLMs in here. I don't know how it would work with Claude Code though.
Okay, thanks.
Yeah.
Hey, Marilyn, there was a question in the chat. Trying to get there. Let's see.
Oh, I didn't look in the chat.
Yeah. Let's see. It just came in while you were answering the last question. Was there training on the Kaggle AI models, and could you use proprietary information? Is what it says there.
I'm sorry, was there training on
On the Kaggle AI models?
Not sure.
Yeah.
That's just where I got the
It's-
data from, and it's like open to anybody that just puts in their email. You can go there and download it. So I'm not sure if I understand the question, but glad to try and answer. Do you want to give me some more info on that?
Nat, was there anything additional to add to that question, or? And then it also asks if you could use proprietary information.
Oh, I think maybe they mean like if you wanted to use, I think I know what you're asking. In one of the examples I mentioned from Syngenta, they're predicting chemical formulations, for example. So you might have proprietary data and like maybe you're concerned about sending your secrets externally, but that's not what's happening. This is a contained system and this is just on my laptop. So I'm not running this on a server. There's no connection to the outside unless I send something out of here. So sure, you could use proprietary information, probably as long as your software is installed on your company computer, right? I hope that answers the question.
Yeah, this is Nat. I was just wondering,
Hey, Nat.
like the front end of the software, is that something you created or was that already part of the model?
No, the front end, you mean the GUI,
Yeah,
this graphical interface?
yeah.
No, the person that created this, his name is Russ Wolfinger, and he is a Kaggle Grandmaster, and he also happens to work for Jump, so he created the front end on this.
Okay, that was my question. If you
Yeah.
want to use the GUI, then would you talk to him or is it just pretty self-explanatory?
If you want to use the GUI, you would just purchase a license for Jump.
Okay.
Yeah. And like I said in the beginning, I think there's other softwares that do similar things, but this is the one that I know and that's
Okay.
worked for me. But yeah, you could purchase a license and then get any extra downloads that you want. This is actually an add-in. That's why it's in the add-ins menu. But yeah, you could just buy a license, download the add-in and use it. And then you
Okay.
could just ask support. And also on the downloads page, Russ made a really detailed video on how to do it and what things mean. And this comes with a really detailed PDF that tells you maybe more than you want to know. I think it's like 40 pages of PDF, so there's a lot of documentation.
Okay.
Yeah. Did
Thank
that
you.
answer your question, Nat?
Yeah.
Okay.
Looks like John has a question here in the chat again as well. It's asking if you could use a drawing with agentic AI to create a perfect first article inspection for modeling.
I'm not sure I understand that question, John.
Yeah, John, do
Sorry.
you want to elaborate?
Well, so
You guys,
if I'm looking at CAD systems, by the way, I've done visual inspection on surface mount. So I was just curious if you could take a drawing which specifies, your fit, form, or function, if you could run it through an agentic program and then create an image, you're doing multiple images for scanning and that to look at the variation in that. But then I was just wondering in my mind if you could do that and then use agentic AI. And this is where our issues with agentic AI right now, because they'll come up with a solution, but then you create what is a perfect first article, and then you would have that as your criteria for doing measurement. It was
Yeah, I'm
just
not sure.
I was
Yeah.
just wondering because what I'm doing is I'm working with a company right now, and one of the issues that we're getting with the agentic is they're using it and they're coming up with the ultimate solutions, but they're not showing all the steps in between it.
Mm,
So I was just
yeah.
wondering, we did this in China where we did we did visual recognition and we didn't call it AI, but we took several physical AI or several physical parts as a first article. Then we used that as the criteria to fill it in to do our measurements and our final inspection quality went off the charts. We're almost at 100%.
Mm.
So I was just wondering if, somebody had done that when you're pulling down and you're looking at so many images and wondering like, wonder if you could use a Genic to do something like that.
I'm not sure. I don't work with any AI automations or agentic AIs. It's only engineers and scientists that want to understand their data. So back to the basics is all I do. So I'm sorry, I don't have an answer to
Oh,
that, John.
no, no, no. I'm a simple guy. I was just wondering. The engineers talk to me, and my eyes rolling back in my head half the time. So I was just wondering.
Yeah, sorry I don't have a better answer for you, John.
Oh, no, no, no. That's probably the answer. People don't know the level of complexity that it takes to go through and develop this. So I think this is a great presentation to really show what it takes to put it all together to
Hmm.
get, to see it on the end, on like the production floor and that.
Yeah, thank you.
Right. Does anyone else have any other questions for Marilyn? All right. Well, thanks, Marilyn. I love seeing a practical example of
Yeah.
something, a tool that we could use out in the field. So again, second time seeing this, and I still enjoyed it just as much. So great job. Thank
Thank you.
you. All right. And if no one has any other additional questions, I will continue on with the section business portion of the program. So feel free to stick around. I do have some additional information and things we'll be doing for the section here in the Phoenix area. So this is the leadership team for 2026. You can go to our Phoenix section page, and I believe all of our emails are linked within the main page there in the Phoenix section. So if you have any questions for us, feel free to reach out. And also my email and a few other emails are listed throughout the presentation. As we're coming up on 2027, I know the region and the geographic centers are starting to look for nominations for their leadership changeover teams. So it's just a good segue for us as well to start looking for volunteers and that are looking to serve within the Phoenix section. So if you have any interest, as we get towards September, we'll start soliciting. You'll see some emails come out from Sam and myself. So, but if you have any interest in the meantime, feel free to reach out to Sam. His email is here on the screen as well as mine. Now, I know I mentioned before the presentation that we have additional opportunities to go in and review presentations. This presentation will be uploaded as well within the coming days by Barbara. So in the event that you are looking for RUs and you need a couple additional ones, you can always go back within our library here and find previous program recordings. Watch those program recordings, and then you can send myself or Jason an email. And Jason's email should be linked within our community homepage here as well, or you can find them in the members section. All of our events, likely most of you found us here on the events tab, so you should be familiar with that. And we have our monthly newsletter that goes out, the Sundial. We have any other additional handouts. We have 1 point lesson plans we put in there, and then as far as mini papers. We are looking to do some in-person events within September and November. So in September, we are trying to work for a book exchange at a coffee shop, potentially a library with here in Central Valley, maybe Scottsdale, Phoenix, Chandler area. We're still working on that location, but I plan on that being for the 12th or the 19th of September. That's a Saturday, sometime early in the morning between 9 to noon is what we're anticipating. So be on the lookout for that. You should see that come out in our Sundial newsletter. Barbara will probably put a blog post out there, and we'll get everything set up so you can be aware and plan. And then we're also going to do a Santan Brewery meetup. We're just confirming the date for November 14th. And again, that'll be an early afternoon event, and then potentially meet up afterwards, maybe for some dinner. But the Santan Brewery will offer a tour of their brewery, and then also talk about their quality system as well. And then in Q1, we're looking at doing an Amazon warehouse tour on the west side, I believe, near Goodyear, I think. All right. Again, our Sundial e-newsletter that comes out once a month, and it just came out, I think, yesterday, actually. So take a look at that. Within there, you'll see this monthly program notification. I put out a message every month as well. We'll have any one-page lesson plans, and then we're also looking to start including some specific articles that are relative to quality, and we'll start including those in our e-newsletter as well. All right. So again, Jason will be sending out your RU certificate. Once we get the listing downloaded, it'll be a RU certificate, a thank you email, and it'll also include a survey. We ask that you take that survey. We usually do pretty good on the number of people that attend and take the survey. So we definitely appreciate that. And then we look forward to your feedback, and we discuss it every month in our leadership team member meeting. And within that meeting, we take and we find programs that you have suggested in there, training events. We'll put in our one-page lesson plans, and we continue to try to tailor based on your feedback so that we can continue to support you guys. So coming up in August, we have the 7 secrets to rocking the audit stage with respect, and that'll be presented by Susan. So if you're interested in auditing, I know we had a few auditors in here tonight. This may be another good one for you. And then here's the list for the rest of the year as far as, excuse me, as far as presenters. Linda Westfall is risk analysis and mitigation. Shireen Yalda, this will be a joint program with the St. Louis section on how to align people, processes, and technology for QMSR. Shireen is, I met her here at the Lean and Six Sigma conference. Very intelligent, and she works in the medical field. So anybody interested in the medical field as well, Shireen will be happy to answer your questions. And then we'll have Gwen Jones for change management, and then Steve Gompertz, again, for QMSR impacts from functional to system thinking. And Jason's also has a few speakers ready for 2027 as well. And once I get that list, I'll get it updated here. All right, here is all of our social media accounts. Feel free to connect with us on any of our social media. I typically post on LinkedIn the program event too. So if you miss it from the events page, you may find it on LinkedIn. All right. And that's a pretty quick wrap up there. Any final thoughts, comments, or questions from the group? All right. Nothing seen, nothing heard. Thank you again. I hope everyone has a great week and weekend. Please again complete that emailed satisfaction survey that you'll get from Jason. He'll probably bug you with it 2 times if he doesn't hear back from you, and then we'll leave you alone after that. But everybody have an excellent night. Thank you.
Thanks much.
Yeah.